Hello and welcome to another Orange Coast College mathematics video. In this video, we're going to learn how to graph exponential functions. Now, before we begin, I'm going to assume that you are somewhat comfortable with the idea of graphing via transformations. That is, if you have a graph of, say, f of x, understand things like how to shift it up or down, left or right, reflect it in the x-axis, and so on. Okay. All right, so if we're given an exponential function, f of x equals b to the x, it's important to remember b must be a positive number, and it can't be 1, because if it was just 1 to the x, it would just be constant. So for an exponential function, its domain is all real numbers, or the interval from negative infinity to infinity. I can plug in any value for x as long as that b is a positive number. Now the range is going to be from 0 to infinity, not including 0, because if b is positive, then any power of b will also be a positive number. Now, in general, the x-axis is going to be the horizontal asymptote when it looks like this. And that's because if you imagine, like, say, b is a number like 2 or 3, as x gets closer and closer to negative infinity, it means like negative 100, negative 1000, right? If you take, for instance, 2 to the negative 1000th power, it's going to be a number that's really close to 0. It's going to be really small. And the larger that exponent gets, negative exponent gets, the closer it will be to 0, which means you're going to approach the x-axis asymptotically. We'll see this in our first example. Okay, here's our first example. We want to graph f of x equals 2 to the x. So the domain and range, as we've already said, the domain is all real numbers. The range is 0 to infinity, not including 0. And the asymptote will be the x-axis, or y equals 0. So I want to graph this by plotting some points here. So if we have f of x, x is the values given there on the table. What is 2 to the x, which would be our y coordinate? So 2 to the negative 3 would be 1/8. 2 to the negative 2 would be 1/4. 2 to the negative 1 would be 1/2. 2 to the 0 would be 1. Okay, 2 to the 1 would be 2. 2 squared is 4. And 2 cubed is 8. So if we plot these points here, so at negative 3, it should be 1/8. That's going to be pretty close to the x-axis. At negative 2, it should be 1/4. That will be also very close to the x-axis. 1/2 at negative 1, and then there. So that's like the first 4 points there. At x equals 1, it should be 2. At x equals 2, it should be 4. And at x equals 3, it should be 8. So it's going to look like this. And pardon, my drawings aren't going to be gray here, but this is just doing it by hand. What are you going to do? So it should kind of look like this. Should be smooth. And it should kind of go up like that. It should get really steep. That's what growing exponentially means. It gets very, very, very steep. It means more than that, but we're not going to go into it here. So as you can see, right, as we travel to the left, as we go along the x-axis to the left, so it's the large negative numbers, we're going to approach the x-axis asymptotically. And as we go to the right, we just grow. It gets very, very steep. It's going to get steeper all the time. Okay. So a couple other things too. This point right here, because no matter what b is here, as long as b is greater than 0, b to the 0 power will always be 1. So in general, when you have b to the x, it's always going to cross the y-axis. The y-intercept is always going to be 1. So basically, this guy right here is important. So that's true kind of no matter what b is. So as we're going forward, we're going to draw more of these graphs. I want you to remember, we have the asymptote. If we shift the graph up and down and all, that asymptote, that horizontal asymptote will shift. And then this point is going to shift as well. Okay, if we shift left or right, up or down. Example 2. All right, so in the previous example, we did 2 to the x. Now, if you remember, the shape of that was kind of like this, And in general, when the base of the exponent, so the base is like the b, when that number is greater than 1, that's going to be the shape. It's going to approach the x asymptotically as we go to the left, and it's going to go up to infinity as we go to the right. But now our base is less than 1. Remember, it always has to be positive, but now it's less than 1. And so what happens here is 1/2 to the x, this is the same as 2 to the negative x. So essentially, if we look at the table of values on the previous example, they're just going to be reversed here. So this is going to be positive 8, 4, 2, 1. This will be 1/2, 1/4, 1/8. So all this really did, when we replace 2 to the x with 1/2 to the x, it's just going to reflect the graph in the y-axis. So if I plot these points again here, we have, let's see, 8, 4, 2, 1, 1/2, 1/4, 1/8. So it's going to look just reversed. So again, my drawing is not going to be great, but we try and just interpolate these points smoothly. Okay, so you can see it's the same as the graph before, except reflected in the y-axis. And so in general, if b is between 0 and 1, the graph will look like this. When b is greater than 1, it will look like that from the last example. Okay, so keep this graph in mind for our next example. Example 3, graph g of x equals 1/2 to the x power minus 2. All right, so the domain is going to be the same here, because that doesn't change just by shifting it at all, because that's all subtracting 2 does. It's going to shift the graph down 2 units, right? So the domain is still negative infinity to infinity. Now, when we have 1/2 to the x, we just graphed 1/2 to the x. I'm going to put a couple of anchor points on this thing here. So one of those points, this was 1/2 to the x, went through the point, went through the y-axis at 1. Okay, so that's going to get shifted down 2 units. So that point is now going to be here, right, at -1. The other thing is the x-axis was a horizontal asymptote for 1/2 to the x. When we shift the graph of 1/2 to the x down 2 units, which we do by subtracting 2, now the horizontal asymptote is going to be this guy right here. So I'm actually going to put that on the graph. I'm just going to do it in red here. So here's our horizontal asymptote. And other than that, the shape of this graph should be the same as the shape of 1/2 to the x. So it should look like this. Let's put one more anchor point on this graph. So we also had, for 1/2 to the x at -1, it would go through 2. So that point's going to be shifted down 2 units. So that point's going to be here. Mostly, I just wanted to make sure we got the x-intercept at the right place, but you don't always have to do this. Okay, so that means the graph should look like this. Now I'm just kind of freehanding this a bit more. It's going to go through those 2 points, and then it's going to approach our horizontal asymptote asymptotically here. So the range now, if we look at the range, it's going to go from -2 up to infinity. So it just moves that interval, the range, down 2 units. So it's going to be -2 to infinity, but the graph can still, the value of the function can never be -2. And the horizontal asymptote, as we've already mentioned, it's going to be the line now y equals -2, right? So horizontal line, so it's going to be y equals, and it's just y equals -2. Every point on that line has the same y coordinate. Okay, example 4. All right, this one's a little bit more complicated. So we want to graph h of x is -3 to the x plus 1 and then plus 4. So our base graph here, right, is 3 to the x. And then we can get, that's kind of what the shape of our graph is going to look like, right? Except we're going to undergo a series of transformations on this graph, and that's going to change sort of how it's oriented in the plane. The shape will be the same, but it just won't be in the same location as the graph of 3 to the x, if that makes sense. Because all we're doing here is we're doing reflections and shifting on this. So we can get to the next sort of stage by replacing x with x plus 1. So let me graph these in stages. So 3 to the x would look like this. So it's going to cross the y-axis here. I'm just going to kind of just dotted line these. Okay, so it looks like that. Now 3 to the x plus 1 is going to shift it over 1 unit to the left. So this guy's going to come here. Its y-intercept, when x is 0, you can find the y-intercept by making x 0. It's going to be 3. It's going to look like this. Sorry, hold on. So it should look like this. That's going to be 3 to the x plus 1. And now to get the next step, we take -3 to the x plus 1. Now to get the graph of that, we take the graph of 3 to the x plus 1 and we reflect it in the x-axis. So what that's going to give us, it's going to go through this point here and this point down here. It's going to look like this. Okay. And then the final step, I'm going to do this one in red because this is our final graph here. It's going to be -3 to the x plus 1 plus 4. So now we just shift everything up 4 units. Now, the first 3 graphs here, all of these guys, had the x-axis as a horizontal asymptote. So that's going to get shifted up by 4 units. So now the line y equals -4, that's our, y equals +4. That is our horizontal axis there, our asymptote, horizontal asymptote. So all the other points are going to get shifted up 4 units. So this point right here is going to be 4 units up. So that's 1, 2, 3, 4. Okay. And the y-intercept goes 1, 2, 3, 4. It's right here. Okay. And it should have the same shape, though, as this guy, just shifted up 4 units. So it looks like this. Okay. And that's the basic idea. So the horizontal asymptote is y equals 4. The domain does not change for any of these problems. They're all the same. So -infinity to infinity. And now we can see the range, right? Where along the y-axis does this lie? So the greatest value it can take on, it can't be 4, but it can be any value that's sort of up to 4. So it can be 4 or less than 4. Any number less than 4 is possible. So the range is just going to be -infinity up to 4, but not including 4. Here's our final example. We want to graph h of x equals e to the x plus 1. Now, e here represents a irrational number, a constant called Euler's number. And it doesn't really matter what it is, but it's, except for that it's larger than 1. So it's approximately 2.71828. Okay. But really, it's between 2 and 3. So essentially, if you looked at the graph of e to the x, it's going to lie between the graphs of, say, 2 to the x and 3 to the x, which basically means it has the same basic shape as those, whereas it's going to go off to 0 as we go to -infinity, and it's going to cross the y-axis at 1, and it's going to go up to infinity as we go to the right. So it looks like that. So really all this is just shift it up 1 unit, right? So it's going to cross, the y-intercept is going to be right here, and then the asymptote is going to be shifted up off the x-axis by 1 unit up. So the asymptote is now going to be the line y equals 1. And like I said, other than that, it's going to have the same shape as 2 to the x or 3 to the x. So it's going to look like this. That's it. That's fine. So let's go over the domain here. The domain, like I said before, for all of these problems, it's the same. It's just all real numbers, or -infinity to infinity. And the range, so the smallest it can be, it can't be 1, but it can be any number that's larger than 1. So it's going to be just 1 to infinity. And as we already mentioned, the horizontal asymptote is y equals to 1. And that's it for graphing exponential functions. So most of this, I think most of the difficulty you'll have in this is transformations of graphs. So the shapes of the basic exponential functions like b to the x are pretty straightforward. Most of the rest of this sort of difficulty or complexity is going to come from transformation. So it might be worth going back to take a look at that if you're having trouble with this. Okay, until next time, have fun.